Hello and welcome to this short video where we're going to be deriving the quadratic formula. Before we do so, we first need to know what the quadratic formula is. Given an equation of the form ax squared plus bx plus c equal to 0 for a, b and c, which are elements of the real numbers, as in a, b and c are some kind of constants that are elements of the real numbers, and a not being equal to 0, then the two values of x for which this solution is valid, as in the two values of x that when you substitute into here and here you get equals 0, are x equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. To start off, let's talk about why we need a to not be equal to 0. In the formula we can see that we have to eventually divide by a, as in we have this minus b plus or minus the square root of b squared minus 4ac divide by 2, and then the whole thing needs to be then divided by a. If a is equal to 0, then we would be dividing by 0 in this formula, which is not allowed. For this reason, when a is equal to 0, we cannot solve the quadratic using the quadratic formula. This does not, however, mean that we cannot solve the quadratic equation like this. It just means that we cannot use the quadratic formula that we have here. Instead, we need to do something like this. If I suppose if a equals 0, then if I write down this equation, we can see how we can find the solutions of it. When a is equal to 0, then a over here in this bit is equal to 0. So therefore what we have is 0 times x squared plus bx plus c equals 0. Now then, no matter what x is, 0 times x squared would be equal to 0. So therefore this whole term here is equal to 0. So what we have is 0 plus bx plus c equals 0, which means what we have is bx plus c equals 0. Taking the c to the other side, we can see that bx is equal to negative c, and dividing both sides by b, we can see that x is equal to negative c divided by b. Therefore, it is possible for us to solve the quadratic equation when a is equal to 0. We just cannot solve it based on the quadratic formula that we have here. So now that that case is out of the way, and we know that we can solve this kind of equation if a is equal to 0, let's try solving the equation when a is not equal to 0. To do that, let's go to a new page and consider ax squared plus bx plus c equals 0 for a not equal to 0. In order to solve this and derive the quadratic formula, the first thing we need to do is divide the whole thing by a, as in we divide the left side by a and we similarly divide the right side by a. Dividing the left side by a, we can see that ax squared divided by a is going to be x squared plus bx divided by a is going to be b divided by ax, and c divided by a is going to be c divided by a. On the right side we have 0 divided by a. Since a is not equal to 0, we don't have 0 divided by 0, and 0 divided by anything that's not 0 is going to be 0. So here we have 0. Therefore we have x squared plus b divided by ax plus c divided by a equals 0. At this point what we're going to do is to take the c divided by a to the other side. Doing so, we get that x squared plus b divided by ax is equal to negative c divided by a. Now, the next thing we're going to do is a little bit of a complex procedure known as completing the square. Some of you may be familiar with it, some of you may not. The completing the square method is based on this simple idea. If I have a square of the form x plus d whole thing squared, when we expand this, we know this is equal to x squared plus 2dx plus d squared. This is what we would call a complete square, as in this set of terms here is the equivalent of a complete square as x plus d whole thing squared. However, instead of this, if we just have something like, let's say, x squared plus 2dx, as in we have an x squared term, we have an x term, but we don't have a constant term, this is what we would call an incomplete square. In order to complete this square, we can see the term we are missing is a plus d squared term. However, we cannot simply add the plus d squared term, because then whatever value we have would not be the same as what it was previously. So in order to add the plus d squared term, what we need to do is add the plus d squared term but then immediately subtract it. This would not change the equation at all, as in if we had something like, let's say, k equal to x squared plus 2dx, adding a d squared and then subtracting a d squared would not change this fact that this is an equal sign here. So then, doing so, we can now have x squared plus 2dx plus d squared minus an additional d squared. At this point, this set of terms is a complete square, as in we've completed the square. We have an extra term minus d squared, but we can ignore that for now and only consider this bit right here. Considering only this bit is a perfect square, as in we've completed the square. And we can see that this perfect square can be written as x plus d squared. So therefore with this we can see that k is equal to x plus d whole thing squared minus d squared. This process that we just did here is what we call completing the square. Now, we're going to be applying that method into this equation here. On the left we can see we have an x squared term and an x term, but we don't have a constant term. What we're going to do now is apply the completing the square method by supposing that this thing is of the form x squared plus 2dx. In which case, to complete the square, all we need to do is add d squared and subtract d squared, at which point this bit here would be a complete square. Now, in order to figure out what we need to add here, we're going to compare this thing right here. Here we can see that in this format, the 2d is equivalent to b divided by a. Therefore, on the side we'll write that 2d is equivalent to b divided by a. Therefore, d is equivalent to b divided by 2a, and therefore d squared is equivalent to b squared divided by 2a's whole thing squared, which is going to be 2 squared times a squared. 2 squared is 4, so we have 4 times a squared. So therefore d squared is the equivalent of b squared divided by 4a squared. Therefore, in order to complete the square, what we need to do is to add plus d squared and subtract plus d squared. So what we need to do in this case is to add b squared divided by 4a squared and then immediately subtract b squared divided by 4a squared. So in the next line, let's do exactly that and write x squared plus b divided by ax plus b squared divided by 4a squared, and then immediately minus b squared divided by 4a squared, and this should be equal to the thing on the right, which is negative c divided by a. Now let's cut out some of this rough work and consider what we have here. Here we know that we have the formula of x squared plus 2dx plus d squared, where d is b divided by 2a. Now we can see that then this complete square can be written as x plus d squared, where d is b divided by 2a. Therefore, this set of terms here could be written as x plus b divided by 2a whole thing squared, and then additionally to that we have the minus b squared divided by 4a squared, and that is equal to negative c divided by a. Let's now erase some of this rough work and continue our solution. Here we can see that this whole thing can be taken to the right hand side. Doing so, we get x plus b divided by 2a whole thing squared being equal to this thing on the right, which is going to be b squared divided by 4a squared minus c divided by a. Our next step is going to be taking these two terms under a common base. The best common base to use would be 4a squared, since here we can see that this base here of a could be turned into a base of 4a squared if we simply multiply the top and the bottom by 4a. Doing so, we can get that on the left hand side we have x plus b divided by 2a whole thing squared being equal to b squared minus c times 4a, which is 4ac, divided by the common base, which is going to be 4a squared. Now we can see we kind of almost have the quadratic formula. We can see the pattern of the b squared minus 4ac, and we're getting close. The next step we're going to do is going to be square rooting both sides. Before we do that, however, I need to bring to your attention this fact. Consider 5 squared. 5 squared is 5 times 5, which is going to be 25. Now consider negative 5 squared. Negative 5 squared is going to be negative 5 times negative 5. A negative number times a negative number is a positive number, and 5 times 5 is 25. Therefore, negative 5 squared is also 25. Now we can see that if we have some number squared and that number is equal to 25, then that number could either be plus 5 or minus 5. So suppose instead of these two, I have the equation x squared is equal to 25. If I'm asked what x is, I know that 5 squared is equal to 25 and negative 5 squared is equal to 25. Therefore, x could either be positive 5 or negative 5. The way we write this is that x is equal to plus or minus 5. This plus or minus indicates that x could either be plus 5 or minus 5. It's one or the other. Now, applying the same principle here. Up here we can see that x plus b divided by 2a whole thing squared is equal to b squared minus 4ac divided by 4a squared. Therefore, the thing on the inside, which is going to be x plus b divided by 2a, could either be the positive value of the square root of this thing or the negative value of the square root of this thing. Therefore, in order to account for that, we write that this value here on the inside is equal to the positive or negative, as in plus or minus square root of b squared minus 4ac all divided by 4a squared. Now, the next thing we're going to do is apply a principle of square roots, where if you have square root of one thing divided by another thing, it's the same thing as the square root of the top part divided by the square root of the bottom part. Therefore, what we have here is x plus b divided by 2a being equal to the positive or negative square root of b squared minus 4ac divided by the square root of 4a squared. The next thing we are going to do is to take an observation. Here we can see we have the square root of 4a squared. The square root of 4a squared is the square root of 2 times a whole thing squared, since we know that 2a whole thing squared is equal to 4a squared. Now, I want to bring your attention to the fact that this could also be negative 2a whole thing squared, which is also equal to 4a squared. So then, which of the two should I put here? Should I put plus 2a for the square root of 4a squared, or should I put minus 2a? Well, as it turns out, it doesn't matter which of the two you put, and the reason it doesn't matter is because of this plus or minus sign. The plus or minus sign essentially destroys the signs of whatever's in front, and due to this, we do not need to put plus 2a or minus 2a, we can just substitute 2a. To show you how the plus or minus sign destroys other signs, I'm going to illustrate that by doing plus or minus 1 times 1 versus plus or minus 1 times negative 1. Considering the two cases, in the case of plus or minus 1 times 1, this could either be plus 1 times 1, which is going to be 1, or it could also be minus 1 times 1, which is going to be minus 1. As for the second case, here we have plus or minus 1 times the negative version of what we had up top, as in negative 1, and doing so, there are still two cases. The first case is going to be plus 1 times negative 1, which is going to be minus 1, or the second case, which is going to be minus 1 times negative 1, which is going to be plus 1. Now here, analyzing the two answers that we get. In the case where we have a plus thing here, we get 1 and negative 1. Considering the minus case, in the minus case, we also get 1 and negative 1. Therefore, whether we have 1 here or negative 1 here, the answers that we get are still the same. In the exact same vein, whether we put plus 2a here or minus 2a here, the answers that we get finally are going to be the same. They're going to be both plus this thing and minus this thing. So therefore, we can just ignore the sign of a directly, and instead of having some absolute value something in here or doing plus 2a in some cases and minus 2a in other cases, we can just put 2a directly, since we know that the plus or minus is going to destroy the sign. Therefore, into here, we could substitute directly that x plus b divided by 2a is equal to plus or minus the square root of b squared minus 4ac divided by 2a. Now, there's one last step we need to do, and that's to subtract this b divided by 2a from both sides. Doing so, we get x is equal to minus b divided by 2a plus or minus the square root of b squared minus 4ac divided by 2a, and now we can see we have a common base of 2a on here and here, which we could take as finally x equals minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So then, that is our quadratic formula, and these two values of minus b plus the square root of b squared minus 4ac divided by 2a and minus b minus the square root of b squared minus 4ac divided by 2a are the two results that are two values of x, for which substituting those values of x into our original equation would give us 0. So then, that is what the quadratic formula is. Before I end the lesson, there's one more thing I'm going to talk about, and that is something called the discriminant. It is this bit on the inside of the square root here, b squared minus 4ac. It is often represented by the symbol delta, as in this triangle here, is equal to b squared minus 4ac. The reason it's called the discriminant is because it discriminates between whether x has a real solutions or not. You see, if b squared minus 4ac as in delta is negative, then what we have here is minus b plus or minus the square root of a negative number divided by 2a. As we know, The square root of a negative number is something called an imaginary number, and an imaginary number plus a real number is something called a complex number. Therefore, x would be a complex number if b squared minus 4ac, as in the discriminant, is a negative number. If instead b squared minus 4ac is equal to 0, then we would have minus b plus or minus the square root of 0, which is going to be minus b plus or minus 0, which is going to be minus b whole thing divided by 2a. As in, we get only one solution of minus b divided by 2a given that b squared minus 4ac is equal to 0. And finally, if b squared minus 4ac is positive, then here we have a positive number whose square root is some positive real number. So therefore we have plus or minus that real number, meaning that there are two values of x, as in minus b plus that square root divided by 2a and minus b minus that square root divided by 2a, which are the two real solutions for which x can be substituted into the above equation in order to get ax squared plus bx plus c equal to 0. I'm not going to go any more in depth than that in terms of the discriminant. I'm going to end it there. If you want to learn more about the discriminant and different cases of quadratics, click this video on the top right here. And that's going to be all for this video. I hope you enjoyed. Thank you for watching and goodbye.